Hello everyone. In this video, we are going to talk about the measurement of the electrolytic conductance. So here basically, if you remember, I told you I'll be discussing how we would be able to calculate a lambda EQ and or lambda molar conductivity. Okay, and if you remember, both these we related with the specific conductivity. So if for a given electrolyte solution you are able to measure the specific conductivity, then you can easily measure the lambda EQ or lambda M. And we know that these specific conductivity can be related to even the conductance, and therefore it is important to know how we can measure the electrolytic conductance. Okay, so for that, basically, if you can see here, we use this particular system where this part of the system is what you refer to as the conductivity cell. Okay, this conductivity cell, as you can see, contains two electrodes, and these are platinum electrodes. And this conductivity cell is covered, these platinum electrodes are contained in a kind of glass which is made up of Pyrex. Okay, and the electrolytic solution for which you are measuring the conductance is kept in this particular cell. Okay, and this cell is then connected to a kind of resistance system, which you might have learned in physics, like if you use a Wheatstone bridge. Okay, Wheatstone bridge is used to measure an unknown resistance. So Wheatstone bridge is what is called, if I recollect correctly, it's called Wheatstone bridge. So it looks something like this. You have some variable resistance, and suppose R2 is an unknown resistance whose resistance you don't know, and these are some of the known resistance. Then this is the galvanometer. So in the null point region, this particular ratio is valid, which is R1 upon R3 is equal to R2 upon R4. So same kind of relationship we use here to determine the conductance of this particular electrolytic solution. So if you can see here, you have this electrolytic cell connected here, and it is the X, given a term X which is unknown. So this conductance we don't know. We have a variable resistance here, which we can keep on changing. Okay, depending upon we can change this resistance. So it is a variable resistance. And then we have in this particular instrument, it's a galvanometer. So you have a rod that is connected to a galvanometer, and you have a point which you can move until you get a null point. But here we replace that galvanometer with a earphone. That is because the current that you use here is alternating current. Usually in galvanometer experiment you use DC currents, but if you use DC current here, you can expect the electrolysis happening of the electrolyte solution. In order to avoid the electrolysis of the electrolyte solution, because if electrolysis happen, then the concentration of the electrolytic solution will change. Okay, so in order to avoid that, here we use a alternative current as the source, and hence we cannot use our normal galvanometer. Rather we use a earphone. Basically here what we do is we'll move this point till we get a minimum sound on the earphone. Okay, so this is the basic setup of the apparatus that we use to measure the conductance. So as you can see, we can once you get, this is the galvanometer, so you can connect it using the Wheatstone relationship. So you can write R upon X is equal to so since this is this is in resistance is in terms of distance, so it is AJ times AJ upon JC. Okay, so we get the ratio in this particular format, that is R upon X. X is the resistance for the conductivity cell, which we don't know. Okay, and R is the variable resistance, which we know because we can vary this resistance, and the value of the AJ, that length, you know, in the same manner JC, you know. So therefore this is the relationship that you get from for the Wheatstone bridge. Okay, the way in which Wheatstone bridge, if you connect the resistance in that format, this is the ratio that is valid at the null point. At the null point, that means the point at which you get a minimum sound on the earphone. Okay, so you get this particular expression, and where R upon X is equal to AJ by JC. So AJ, you know, the length you can measure. JC, you know, again the length you can measure. R is a variable resistance. It's the standard resistance box, so you know the value of the R here. So only unknown is the resistance of the electrolytic cell or the conductivity cell. Okay, so if you rearrange this, you can bring this R term here, so it becomes 1 upon X equal to 1 upon R into AG by GC. Okay, now this 1 upon X, that is 1 upon resistance. Now X is the resistance of the conductivity cell. So this 1 upon resistance, you remember we have related to conductance. We have related it to conductance. Okay, and therefore you can measure the conductance using this particular apparatus. Okay, so important thing in this is this conductivity cell, which is actually made up of two platinum electrodes. In between it you contain the electrolytic solution, and it's made up of Pyrex glass. Okay, so this is the setup that we use to measure the conductance. So you don't have to remember these procedure, but you should understand how we can use this instrument to calculate the value of conductance. So once you know the conductance, you can easily measure the conductivity, because it is related to conductance using this particular expression. Now these L and A are basically the length of the electrode, at the same time the area, cross-sectional area. But here you should know that uh, it's not always you can measure the L and A accurately for these platinum electrodes. So more appropriate term that we use is a ratio L by A, that is the that is kind of constant for a particular conductivity cell. Depending upon which conductivity cell you use, the L by ratio would be constant, and it is known. And this L by A ratio is what you refer to as the cell constant. This is what you refer to as the cell constant, and you represent it using a letter G star. Okay, so this expression now can be reduced to K, that is conductivity, is equal to conductance times the cell constant. This is very important expression to calculate the uh, conductivity, because we know once conductivity is known, you can easily calculate the lambda EQ as well as lambda M. Okay, so this is how actually we measure the lambda EQ and lambda M for different electrolytic system. Okay, now let's focus quickly on some of the numerical, and then we'll wind up this video. So if you can see here, we started with so the first question that we see here is if the specific conductivity of n by 50 kCl solution at 298 Kelvin is this value, then and resistance of the cell containing this solution is 100 ohm, calculate the cell constant. So what all information, so as I told you, the first thing that you should always do is calculate the given factor. So if you look at the given factor, it's pretty simple. You're given the normality. So n is given, n by 50. And then we are given the specific conductivity, that is K. Okay, K value is given to be 0.002765 per ohm per centimeter. And then you are also given resistance here, and the value of resistance is 100 ohm. So R is given to be 100 ohm. So what you have to calculate here is the calculate the cell constant, that is G star is what you have to calculate. We just now learned an expression where uh, conductivity is related to conductance and the cell constant. So you have K is equal to C times G star. So we have to calculate G star. So it would be simply K upon C. Okay. Now K is given to us. So this is the value of K given. Okay. Now C is conductance, and you know conductance is 1 upon R. Resistance is given, so it is 1 upon 100. So you got this value as 0.01 per ohm. Okay. Now when you solve this, you get this particular value for the cell constant. So if you substitute these values, you will get directly the actual unit for the cell constant. So this is the first numerical, and I hope this is clear to all of you. Okay, so again in the numericals, the first thing that you should always do is write the given formula and then try to given things in the numerical, and then try to find out the formula that we use to solve that particular problem. Okay, now let's look at another example. This is another question. As you can see, we have given the 0.5 normal solution. That means normality is given as 0.5 normal of a salt placed between two platinum electrodes. So the solution is placed between two platinum electrodes having a length of 0.2 centimeter, and the area of cross section is 4 centimeters square. So that means L is given to be 2 centimeter, area is given to 4 centimeter square, has a resistance of 25 ohm. That means R is given to be 25 ohm. We are asked to calculate the equivalent conductivity of the solution. So that means we are asked to calculate the lambda EQ. Okay, so if you have to calculate, so that we are given facts we have written. Now we will try to find out the formula to calculate the lambda EQ. So you know here lambda EQ is equal to K times 1000 upon normality. Okay, now K is not known, okay, but normality is known, so we have to find out the value of K. Now you know K is related to resistance using this particular expression. This particular expression you know. Okay, so K is equal to 1 upon R into L upon A. R is given to be 25 ohm. L is given to be 2 centimeter, then 4 centimeter square. When you can put these whole thing here as a value of K. So this whole value as such you can put in as K. So that is what I have done here. 1 upon 25 ohm multiplied by 2 centimeter upon 4 centimeter square multiplied by 1000 centimeter cube. This is centimeter cube divided by normality, which is 0.5 gram equivalent. So that is what is written here. So when we solve it out, you should get ultimately 40 Siemens centimeter square per gram equivalent. So this is what you get for this is how you get the lambda EQ. So it's pretty straightforward, nothing complicated. Okay, now let us look one more example and then we will wind that up. So here in this expression you can see the potential difference of 20 volt applied to the ends of the column. So that means you are given a voltage of 20 volt. That means E is given to be 20 volt to the ends of a column of m by 10. So that means molarity is given to be m by 10. So apply to the ends of the column. So the length is given, that is L is given, no, diameter is given to be 4 centimeters, so D is given to be 4 centimeter, and then length is given to be 12 centimeter in length, so L is given to be 12 centimeter, and then you are given current as 0.20 ampere. Okay, so we are asked to calculate the specific conductivity, that is K, and also the molar conductivities, that is capital lambda M. Okay, now again, first thing we have done is given facts we have written down. Now we will write the formula. So if you look at the formula here, it's pretty straightforward. If you want to determine K, use this particular formula. If you are given the value of lambda M, you will use this particular formula. Okay, and because this is actually K equals to C times L by A. Okay, C means 1 upon R. Why I wrote it as 1 upon R is because that would be easy, that we can calculate. Now you will understand why I have written it in this particular format. Okay, so these are the expressions. So first let us try to calculate the specific conductivity. Okay, once you understand that, then it would be pretty simple. Okay, so what you see here is, now here we have to first calculate R. We are given L. L we know. We don't know the value of R. We don't know the value of A. Okay, R is from Ohm's law we know it is E upon I. We are given voltage. We are given current. So you can easily calculate the resistance 100 ohm, and that's why I wrote it in this particular format. This 100 ohm you can substitute here. Now we have to know the value of A. If you remember, in the question you are given the diameter. Okay, so diameter, so we are talking about the cross-sectional area. Cross-sectional area you are talking about, you are given the diameter. So radius would be simply D by 2, and the area would be simply, since it's circular, the area of cross section is circular, therefore the area formula used is pi r square. This you know, you have been learning about the various shapes and the area, so you know that. So pi r square, so it is simply pi multiplied by 4 by 2 the whole square, so it comes out to be 4 pi, and that you can substitute here as A. So substituting all the values, as you can see here, hope you can see this. So what you see here is the when you substitute all these values, you get 3 upon 314 per ohm per centimeter. Ultimately you get the value here. Now once you get the value of K, it is very easy to find out lambda M, because you are already given the value of molarity in the question. So molarity is already given as 1 upon 10. Okay, so therefore it is pretty straightforward. So you can see, when you, it is kappa times 1000 by M. So here kappa is, I have taken this particular fraction, 3 upon 314 multiplied by 1000 upon molarity is 1 upon 10, that is 0.1 mole. Okay, when you solve it out, this is the value of the molar conductivity that you receive. So these numericals are pretty easy to solve. An important thing is, when you see these questions, oftentimes it looks very complicated, but once you write all the given facts and what you have to find out, then if you are aware of the formulas, you can easily substitute the values and you can get the results. Okay, so that's all in this particular video. We'll see in the next video more related to electrolytic conduction. So thank you and have a nice day.